Hi everyone. So we're getting close to get back to school, I think. No official notification yet, but so maybe I won't have to do these for much longer. We shall see. But this week's lesson or assignment is about electrical and electronic components. Easy for me to say. Now this is building up to. I keep talking about it over the last few weeks about electronics, and this is what we're building up to. Electronics is probably going to be an easier thing to do when we're back in school, but we'll get there, and we'll lay the groundwork from doing this stuff. Okay, so all this PowerPoint is going to focus on is like symbols and components, electronic or electrical components. Now, the first couple of slides is just very quick. We can rattle through this because it's just revision of stuff that you should already know. So that's the symbol for a cell. And remember, the big line here represents the positive end of the cell, and a battery is when you have two or more cells connected together. So this is a symbol for a battery, and the SQA are quite particular about the exact symbol. There should be 4 dashes there. And remember, positive line, 4 dashes, positive line, negative line, like that. And these produce DC. Remember, we've looked at AC and we've looked at DC. So batteries and cells produce direct current. They store chemical energy, which gets converted to electrical energy. And excuse me, that's that. Lamps or bulbs. Lamps is I think more usual SQA term. So we talk about lamps. That's the symbol. You need to remember the symbol, and all it does is it converts electrical energy into light. It will produce heat as well. And later on, we're going to look at something that doesn't produce quite so much heat. Still gives off light, but doesn't produce as much heat. So lamps are not very efficient from the point of view of converting electrical energy into light, because usually they produce a lot of heat, and it's because they glow white hot that they produce light. But lamps are not very efficient. Switch, obvious symbol. Basically, if you open the switch, that breaks the circuit, and if you close the switch, then it makes the circuit. So switches cut off the current by making or breaking the electrical circuit. And ammeter and voltmeter we've looked at a few weeks ago. Ammeters to measure current, and they're connected in series as part of the circuit, remember, and you have to break into the circuit in order to add in the ammeter, whereas the voltmeter measures the potential difference or voltage across 2 points. So you connect the voltmeter in parallel with whatever you want to measure the voltage of. So you need to get these 2 meters clear in your head. Ammeters in series, voltmeter in parallel. Resistor, reasonably recently we did this, that resistors are things that oppose the flow of current. And so the bigger the value of the resistor, then the bigger the resistance and the smaller the current. So remember, the resistance and current is a kind of inverse proportion type thing, and so you have to be aware of that and look into that in more detail. Variable resistors are basically a resistor where you can change its resistance, and for doing various experiments excuse me again, for doing various experiments where you want to alter the current and the voltage, then a variable resistor will do that, because you're changing the resistance in the circuit, and therefore that would change the current in the circuit and also affect the potential difference across the components in the circuit as well. So it's a variable resistor is a way of doing experimental work where you want to change the current by various points and then measure the current and voltage. A motor, electrical motor, is straightforward. It just converts electrical energy into kinetic energy. So loads of things in the house have got electrical motors in them: hair dryers, washing machines, microwave. Basically anything that produces movement from electricity will have some kind of motor, probably. And motors generally produce circular motion, so again, excuse me. So you just need to be aware of that. So this is a new thing that we probably haven't mentioned before. This is going to come into it over the next couple of weeks, which is a thing called a thermistor. Now the symbol you can see looks like the symbol for a resistor, so it's similar to that, but then it's got this funny wee bit going through it and there's a T next to it. Now that means it's a thermistor, and the name suggests therm is to do with heat or temperature, and istor comes from resistor. So it's a heat sensitive or a temperature sensitive resistor. Its resistance changes with temperature. We'll do a fair bit more on that. That's part of the sensing circuits that I've spoke about in the past. Okay, and then we have a thing called an LDR, or a light dependent resistor. Again, it's got the symbol for a resistor. The two arrows going in the way indicates that it's going to react to light. So light dependent resistor, as the name suggests, it's a resistor whose resistance varies with the amount of light level. And these two are part of sensing circuits, which I have mentioned in the past, but we're going to move on to do in more detail over the next wee while. Fuses, this was in last week's assignment. Not going into this in too much detail. Basically, it's a thin piece of wire which is a protective device that stops the flex from overheating, protects the wiring from going on fire, and then the general rule, which I'll just repeat again, no reason why not, it's a learning outcome, that if the appliance has got a value, a power rating of about up to 720 watts, so low power, then you would use a 3 amp fuse, and if the appliance is more than 720 watts, then generally you would use a 13 amp fuse. Now that's a bit of a sweeping generalization, because there are some things where they've got a low power, but they have a surge current at the start. I don't want to overcomplicate things. I don't think you would get asked anything like that. So basically, this is the kind of general rule. Loudspeaker. Main thing you need to recognize about this is what the energy change is. So a loudspeaker converts electrical energy into sound. I've got loudspeakers in my ear right now, and that's the symbol. So you have to be aware and recognize the symbol. There's no two ways about it. You have to learn the symbols that we're looking at here. Microphone, I've also got a microphone here. That's the symbol, and the energy change involved in that is obviously sound. So my voice is producing sound, and it gets changed to electrical energy, which travels along the wires and hopefully comes out your loudspeakers at home. So the relay, now this is a complicated, or a reasonably complicated piece of electronics. Again, just mentioning it in passing just now, we'll do more about what a relay, how it operates, why we have a relay in a kind of future assignment, but I'll just now briefly kind of talk about what it is. So it's an electrically operated remote switch, really. And the symbol looks really complicated, but basically what you have, if you imagine the dotted line represents where the relay is. And the relay consists of this symbol here represents a coil of wire, and it's connected to a circuit here. Now, not showing the circuit, but that would be a low voltage power supply, okay? And so what that happens is when you pass electricity through a coil of wire, if you remember back to first year or second year science when you did the electromagnets, if you pass current through a wire or through a coil of wire, it becomes a magnet or an electromagnet. So what that then does is this becomes magnetic, and in the other circuit, now this circuit on the right hand side, which is a completely separate circuit, the dotted lines are no electrical connections, it's really just to show the extent of the relay. But this circuit on the right hand side would be a high voltage, high current circuit. But when you operate the low voltage circuit on the left hand side, the coil becomes a magnet, and what that does is it closes that switch. And so therefore you're switching on this circuit on the right hand side. So your question might be, well, why don't we just have a switch? Well, the reason is because it could be a cost thing, because you want to have low voltage, low current wire, which is thinner and cheaper to operate something which has got high voltage, high current. The high voltage, high current wiring would be much thicker, much more expensive, and so therefore that's why you limit the amount of high voltage, high current wiring you have on this right-hand side. But as I say, we'll discuss this in more detail at a future assignment. Okay, solar cell, or photovoltaics as they call it in America. Solar cells convert light into electrical energy. So that's the symbol for a cell, and the two arrows, when the arrows are going in the way like that, that means it's reacting to light. So this is operated by light. So this is a device that converts light energy into electrical energy, or solar cell. Diodes. Now, I'm just going to mention this one in passing. We're going to look at LEDs in a bit more detail in the next bit. So basically a diode only allows current to pass in one direction. Now, as far as you're concerned, that's really all you need to know at this stage. That's the symbol. Now, one end has to be connected to the positive terminal of a power supply, and one end has to be connected to the negative, and that's the way around it. Basically, what you have to do is memorize this again and recognize when the diode is connected the right way around. If you connect a diode the wrong way around, it won't conduct, won't let current pass through. So this would need to be connected to like the positive end of a cell, and this end would need to be connected to the negative end of a cell for the current to flow properly. But what this is building up to is something called an LED, which is still a diode, so it only allows current to flow in one direction, but and the arrows going out the way shows that this is producing light. So this is a diode that when it's connected into a circuit the correct way around, obviously, for the current to flow, it generates light. And LEDs are becoming much more common in houses. Most household lights are LEDs now. You can't get filament lamps now. They're kind of not on sale much anywhere. So most lights in the house or whatever, in cars, traffic lights, a number of different places are these light emitting diodes. And because they only operate using a very small current and voltage, so they're much more energy efficient than a lamp. Remember way back at the start of this, I spoke about a lamp produces light because it glows white hot and produces a lot of heat. That heat's wasted energy. LEDs do not produce a lot of heat. They produce light and therefore more energy efficient, and that's why in this country that generally it's LEDs that you're using in your lamps and whatever else. Okay. Now a wee bit more about LEDs. The last part of this is all about LEDs, and the very common type of question is to do with this thing here. So this is a circuit where you would have an LED connected. So first thing to recognize, is it connected the right way around? Well, remember, this end of the LED has to be connected to the positive end of the battery, so it is. This end is connected to the negative end of a battery, so therefore this LED would work, current would flow, but they always have this resistor in series with it. And it's a protective resistor, because if this was a 6-volt battery, for example, LEDs generally work around about on 2 volts. And so therefore, if you connected it straight across this battery, there'd be too large a current, too much voltage across the LED, and it would be damaged, if not stop working altogether. So circuits, and it's a common kind of question, is that you get asked about this resistor, and as I'm going to show you later on, how you actually calculate the value of that resistor. So, as I said already, LEDs require a certain voltage. We'll call that the VLED. So that's the voltage across the LED, and a certain current to operate. That would be I LED, right? So this is linking into stuff that we've been doing over the last wee while, that basically it's a voltage divider circuit again. So remember, voltage divider circuits is where you have a supply voltage and it splits up across the two components. Now in this case, in the normal voltage divider, that would be another resistor, but the LED will have some resistance, but we're not bothered about that. All we know is that the voltage will split up. Some of it will go across the resistor and some of it will go across the LED. And the value of the resistor is picked so that you get the correct voltage across the LED. So this is what this wee equation here is telling you that the voltage across the resistor would be the voltage from the supply minus the voltage across the LED. The other way to write that would be that the voltage across the LED plus the voltage across the resistor would add up to the voltage supply. This is going to come into the worked example I'm going to do in the next page. And key thing to also recognise, perhaps, it's kind of obvious, this is a series circuit, so therefore the current going through the LED would be the same current that goes through the resistor, okay? And we're going to use this relationship, Ohm's law again. Whenever you want to calculate the value of this resistor, you have to remember you have to use the voltage that's across the resistor and the current through the resistor, which would be the same current as through the LED. Okay, so this is kind of giving you the rules and regulations of how to answer these. In the next page, we're going to do an actual worked example. So here is the worked example. So we have a 5-volt battery. I've just drawn a cell because it was easier for me to draw. We've got a resistor here. Remember, this resistor is here as a protective resistor to limit the current going through the LED or the voltage across the LED. Is the circuit connected the right way around? Will it light up? Well, yep, because remember that end of the LED should be connected to the positive. It is. So this question is all about calculating what R is. I haven't written that up there, but that's what we're going to do. Now, a bit of information from the question would be, you're told the LED in this circuit has a normal operating voltage of 2 volts and the current going through the LED is 12 milliamps. So the question is asking you to find resistance. Now this is the first place that people make mistakes because you've got a voltage there, you've got a current there. So a lot of people just do, okay, it's 2 divided by 12 milliamps and get an answer. Now that is not the resistance of the resistor. That is going to give you the resistance of the LED, which is not what we're asked for. So the question is, oh, there you go, there's the question there. Calculate the value of the protective resistor that's required in this circuit. Very, very common question. I think if you look back over the last 5 years worth of past papers, I would say generally every single past paper will have a question like this or similar. Okay, so it's a really important that you kind of understand how to do it. It's not difficult, it's just a process that you have to do. So first thing you need to do, remember, if we want to find the value of that resistor, from the previous slide, we need to know that voltage and we need to know the current through it, because if you want to find the resistance here, you're going to do R equals V over I for that part there, for the resistor. So the first thing we need to do is work out what the voltage across the resistor would be, and that's going to be the reading on the voltmeter. There's no reason why I put a voltmeter in there, just for ease of reference really. So remember, it's a voltage divider circuit, so the voltage across the resistor and the voltage across the LED must add up to the supply voltage, which is 5 volts. So in this case, we know that the voltage across the resistor must be the 5, take away the 2, which is 3 volts. Now that's the key part to this whole question, because in reality with this question, there's 3 voltages you could work out. So you've got the 2 volts from the LED, you've got the 5 volts from the battery, but the one we have to use in the calculation is none of those two, it's the voltage across the resistor. So if that's 2 volts across there, 5 volt battery, then that has to be 3 volts. And then it's just a straight Ohm's law question from there onwards. The LED current is 12 milliamps, so that's the current going through the LED, but that also means that's the current through the resistor. So therefore, the voltage is 3 volts, the current is 12 milliamps. Now remember, I have to convert that into scientific notation, so that's 12 times 10 to minus 3. Another common mistake, people will just put in 12 there, and that gives us an answer of 250 ohms. So the value of the protective resistor in this circuit is 250 ohms. So that's the start of what we're going to do this week. I'll set you some more questions on that stuff, usual stuff about Thursday. There'll be a wee quick quiz, and then we'll take it from there. Okay, so hopefully you can catch up with me on the live lessons on Monday, where I just talk through this again, maybe in a wee bit more detail, maybe put slight different slant on various things. But that's there, and also don't forget that we've got the live drop-in sessions on a Wednesday. And I'm also available emails or on the chat through Teams. Okay? So catch you next week.